In this video, we're going to work up a problem that's kind of like question 7 from the chapter 8-1 problem sets. This won't be exactly the same, but it's a similar idea. And so this is a question about finding the pH of an acid solution using activities. So there are two parts to this question. The first part says, what is the activity coefficient of the hydronium H+ ion in a solution containing 0.050 molar HBr, that's hydrobromic acid, and also 0.017 molar in sodium sulfate, Na2SO4. So let's work the first part of that problem first. So we'll do part A here. All right, so we're looking for the activity coefficient, the gamma value of H+. And we know a couple ways that we can find gamma values. So let's see if we can get lucky and look it up in a table. But you know that first off, we need to know what is the ionic strength. So we need to use the equation for ionic strength. So let's think about all the ions that are in our solution and what the molarities are. So we've got 0.05 molar HBr. HBr, hydrobromic acid, is a strong acid. So strong means it's a strong electrolyte. So it's going to completely break up into its component ions, the hydronium ion and the bromide ion. And since this is a 1-to-1 ratio, their molarities are going to both be 0.05 molar. So we know both of those molarities, 0.050 molar. And then the other thing that we have in our solution is this sodium sulfate, right? So 0.017 molar sodium sulfate, Na2SO4. And so we know that sodium sulfate is an ionic compound. It's a strong electrolyte. All sodium salts are soluble, so it's going to dissolve in water and break up to give you sodium. There are going to be two of those by the stoichiometry, so two sodium pluses and one sulfate, SO4, 2 minus. So what are the molarities of these going to be? The sodium is going to be 2 times 0.017 molar, and then the sulfate, since it's just 1-to-1, is going to be 0.017 molar. All right, so now that we've got the molarities figured out, we can plug them into our equation for ionic strength. So ionic strength is 1/2 times the product of the concentrations times the charge squared, all added up. So let's say our first ion is the H+, so we've got 0.05 molar times the charge, which is +1 squared, plus for the bromide, 0.05 molar times the charge, which is -1 squared, plus for the sodium cation, we've got our 2 for the molarity times 0.017 molar. So the 2 again, that comes from the stoichiometry that we have 2 sodiums for every one of these sodium sulfates that dissolve. And then the charge on sodium is +1, that gets squared. Then we need the molarity of the sulfate, so that's 0.017 times the charge, which is -2 squared. All right, so then we do all the math inside here. So for the first term, we get 0.05 times 1, 0.05, plus 0.05 times -1 squared is still 1, so 0.05. Plus, and then here we get 2 times 0.017 times +1 squared, which is just 1, and that's 0.034. And then last we get 0.017 minus 2 squared is 4, so that's going to be 4 times 0.017, which is 0.068. So now we need to add up all those numbers, and then we're going to divide by 2. So 0.05 and 0.05 gives me 1. And then we add 0.034 and 0.068 to that, and we're going to get 0.202. Then when we divide that by 2, we get 0.101, which is pretty close to 0.1 molar. And that's good because that's a value that we have in our table. So now we just need to go to our table and look up the corresponding activity coefficient for H+. So let's go to our table. So here's our table. So here are our columns for ionic strength. Here is 0.1. Here's H+ right at the top, so 0.83. So for part A, the answer to the question, what is the activity coefficient of H+ in the solution? It is 0.83. Remember, this is a unitless number, so we don't have to write down any units. So very good. There's the first part of the problem. So now we need to go about finding the pH, right? So we're going to use this fancier definition, this better definition for pH. Why is it a better definition? Because it's pretty close to what a pH meter would measure. So a pH electrode is sensitive to the hydrogen ion activity and not the hydrogen ion concentration. So pH, by this new definition, is the negative base 10 logarithm of the hydrogen ion activity. And so what is the hydrogen ion activity? So remember, activity is always concentration. So we're going to need to know what is the molarity of the H plus ion in solution. We already figured that out from up here, part A. And then we're going to multiply that by the activity coefficient. So activities are always concentration times the activity coefficient. So to find the pH of the solution, we need to take the negative base 10 logarithm of 0.05 molar times the activity coefficient, 0.83. So that's going to be the negative log of 0.0415. And we take the log of that, and we get multiplied by minus 1. That will give us 1.38 as our pH value. And so that's all there is to that problem. So we just have to use our different definition that includes activity coefficients and activities. So that's why we needed to know the activity coefficient, so we could substitute it in to this expression. Because we already knew what the molarity of the H plus was, because HBr, hydrobromic acid, is one of the strong acids that we've memorized, which means it completely breaks up into its ions, H plus, and whatever the anion is, bromide in this case. So that's how we work that problem.